Use related rates to solve problems involving area. Alright, so today we are diving into related rates. Related rates is one of the more challenging topics in calculus, so if you are struggling with any of these examples or any of these concepts, please set up a time to come see me. Let's straighten it all out, because related rates, they are tough. But hopefully with the more practice, the easier they will get. So, first off, what are related rates? Well, related rate problems involve finding the rate at which a quantity changes by relating two or more other changing quantities. So there's multiple things changing in these problems, and we are trying to solve for just one of them using the other two. So related rates are often changing with respect to time, and that's key here because we are going to want to set up the problems with that in mind. So in all of our problems, or all the problems where our related rates are changing with respect to time, t is going to be our input, which means any quantity that changes will need to be written as a function of time. Now, not every quantity or not every variable in this problem is going to change with respect to time, but the ones that do will require us to change those functions. Alright, so for example, height is an object that is changing, so therefore we need to make it h of t, where t is the input and height at that particular time is the output. So again, height's a function of t, we write it as h of t. So for example, if we had t equals 14 years, then in an example, h of t could be 62. Another completely non-related example, if t is 18 years, then h prime of t would be 74 inches. So again, just two examples of t versus the function of t. Alright, so then we need to review what is rate of change. Well, rate of change is the rate at which a function changes based on the time that passes, because again, we're defining things with respect to time. So, i.e., how much does the output change when we change the input? Alright, so going back to way at the beginning of the semester, when we first started talking about derivatives, what is another word for rate of change? Well, hopefully this has been drilled into your head by now, either by me or by a previous mathematics teacher. Rate of change is the same thing as slope. And in calculus, what does slope equal? Well, slope equals the derivative. So again, for all of these, we're trying to find the derivative. In order to find the rate of change, we do need to find the derivative. So therefore, rate of change equals derivative. Boom, done, moving on. Alright, so let's take a look at our first example. A small rock is being dropped into a lake. Circular ripples spread over the surface of the water, with the radius of each circle increasing at a rate of 3/2 feet per second. Find the rate of change of the area inside the circle formed by a ripple at the instant the radius is 4 feet. Alright, so the first thing I like to do in these types of questions, I like to draw a picture so that I can really kind of understand and visualize what is going on. Alright, so we're told that we have circular ripples. So the first thing I'm going to do is I'm going to draw a circle. And we know that the circle has a radius. And we are told that the ripples spread over the surface of the water, with the radius of the circle increasing. So we have a radius, and we know that the radius is then increasing or getting larger at a rate of 3/2 feet per second. Now we want to find the change in area, which also means that the area, or the outside of the circle, is changing. So therefore, the circle is spreading out. So before we can dive in and do anything, we need to figure out what formula we're going to use in order to solve this related rate. And the formula we're going to use is going to be a circle, because we know the circle is expanding. So the area of the circle, hopefully you remember by now, is A equals pi r squared. Now, after we identify the circle, we need to identify which of these variables have moving parts. So we know that the area changes, the area is increasing, and we know that the radius is increasing, and it tells us that from the problem. It says increasing radius and change of area. So we need to rewrite the a and the r to reflect that, meaning the area and the radius change with respect to time. So I'm going to write this as the area as a function. So it's going to be a with respect to t, or the area where time is the variable. And that's going to equal pi times, we said, r. The radius is also increasing, so r is also a function. So we're going to rewrite this as r of t, because the radius changes with respect to time, and that'll be squared. All right, now that we have turned all of our variables into functions based on the ones that change with respect to time, now we can take the derivative of both sides, because remember, derivative represents rate of change. So the derivative of a of t is going to be the derivative of function a with respect to t, and that's going to equal. And now we have to take the derivative of pi times r of t squared. So in this case, pi is just a coefficient. So to take the derivative of pi r of t squared, we just need to use the power rule, which says move the 2, multiply it to the front, and subtract by a power of 1. So this is going to give us 2 pi times r of t. But since we took the derivative of a function, r of t, we also need to multiply by the derivative of the inside then. And the inside we know is r of t. So the derivative of r of t is going to be the derivative of r with respect to t. So now we have dA over dt is equal to 2 pi times r of t times dr dt. And let's take a look and let's just remember what these represent. So the derivative of a represents the change in area. dr dt represents a change in the radius. And then r of t is the radius at some points in time. So now we just need to pull the information from the problem, substitute them into our appropriate variables, and then solve for the remaining one. Alright, so we know that dr dt is increasing at a rate of 3/2 feet per second. And we want to find the rate of change of the area inside the circle formed by a ripple at the instant the radius is 4. So therefore we know that dr over dt is going to be positive 3/2 because it is increasing. And we know that r of t is going to be 4 because that is the point at which we want to find the change in area. So now we can substitute those values in. So we're going to get dA over dt is equal to 2 times pi, and I used the wrong color for 2, sorry, 2 times pi. And we know that RT we said was 4, and dr dt we said was 3/2. And now we can just simplify. So dA over dt is going to be equal to, let's see, 8 pi times 3 over 2 is going to be 24 over 2, which is going to give us 12 pi, which is going to be approximately 12 times pi is 37.7. And let's see, this is going to be feet squared per second. So you have 37.7 feet squared per second. You could also write the answer as 12 pi feet squared per second, because 12 pi is the actual exact value, whereas the 37.7 feet squared is the approximate value. Alright folks, and that is our first related rate. Not too difficult, so let's move on. Let's take a look at another one. Alright, so in this question we have a circular pool of water is expanding at a rate of 16 pi inches squared per second, or squared inches per second. At what rate is the radius expanding when the radius is 4 inches? So we have another circle problem here. So we can draw our circle, and we know that the circle has a radius. And we know that the radius is, we know that the circular pool of water is expanding at a rate of positive 16 pi square inches per second. So we can draw that in there, 16 pi. We know the radius, is equal to 4. And then we're trying to find the change in radius, dr dt. Alright, so again, since we're looking at a circle, we're going to be using the area of a circle formula. Area is equal to pi r squared. And now let's rewrite our variables that are changing to represent time. So we'll turn them into time functions. So a of t is equal to pi times r of t squared. And now we can go ahead and take the derivative, because again, we're trying to find a rate of change. So it's going to be dA over dt equals, and then again, just as a reminder, we are going to use the power rule and then the chain rule. So power rule brings the 2 to the front, subtract 1 from the old power. So we're going to get 2 times pi times r of t, and then times the derivative to the inside using chain rule, dr dt. Alright, now we're just going to plug in our results, chug, and find our remaining variable using algebra. Alright, so the 3 variables we have left are the change in area, the radius, and the change in the radius. And let's see, according to our problem, we know that the area is expanding at 16 pi squared inches per second. We know that the radius is 4, and we want to find what is the rate the radius is expanding. So that's our variable, dr dt. So let's substitute these other values in. dA dt is 16 pi. That is going to equal 2 pi times 4, because again we know the radius is 4, and then times dr dt. And now we just have algebra. So let's see, go ahead and start rewriting this. So we're going to get 16 pi is equal to 8 pi dr dt. So then we can divide both sides by 8 pi. So the 8 pi will cancel out on the right, and 16 pi divided by 8 pi is going to be 2. So therefore dr over dt is equal to 2. And since the radius is one-dimensional, that means that our it's going to be inches as opposed to inches squared. So we're going to have 2 inches per second. All right, and there you go, folks. 2 rate of change problems down. All right, so this next one is going to be a little bit different, but we're still dealing with area. It says the area of a square is increasing at a rate of 190 square inches per minute. What is the rate of change of the side of the square when the side length is 5 inches? Alright, so just like before, I'm going to draw a picture. And we basically have a square here. And what do we know about the sides of a square? Well, we know that the sides of the square are all equal. So side, 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 side. And again, we're told the area of the square is increasing. So we can draw our little red arrows. And since the area of the square is increasing, the rate of change, or the sides, also have to be increasing. Alright, so we're told that the area of the square is increasing at a rate of 190 squared inches per minute. And let's see, what is the rate of change to the sides of the square when the side length is 5 inches? So we know that the side length is 5 inches. Alright, so now we need to figure out what our formula is we're going to use. Now, if you don't remember what the formula of a square is, or for if you don't remember the formula for the area of the square, that's fine. Remember, a square is just a rectangle. And the area of the rectangle is length times width. And I'm not sure why I just wrote volume. Sorry, area is equal to length times width. And then in a square, the length and the width are both the same. So we're going to call the length S times the width, which is also S. So therefore, the area of a square is going to be the side squared. Alright, so now we just have to figure out which one of these variables change. Well, in this case, both the area is changing and the length of the side is changing. So we can rewrite those both as functions of t, not 2. Sorry about that. And now I can take the derivative. So we're going to have the derivative of the area with respect to t. And that's going to equal 2 times s of t times ds over dt. Because remember, we needed to use the power rule to move the 2 to the front. We subtracted 1 from the exponent, and then we multiplied by the derivative of the inside. Alright, so then we have our variables here. We have the change in area with respect to time. We have the side length at a particular time. And then we have the change of the rate of change of the side. Alright, so we are told that the area of the square increases at a rate of 190 square inches per minute. So dA dt is going to be 190, and I'm not even sure what I was writing there. And it says what is the rate of change of the side of the square, so we don't know ds dt, but we do know the side length is 5 inches. So now we can come in, we can substitute our values and solve for our remaining variable. So we're going to have 190 is equal to 2 times s of t, we know is 5, and then we are trying to find ds dt. So I just need to solve. So we're going to get 190 is equal to 10. Let's put that in purple. 10 times ds dt. Divide both sides by 10, which is going to give us ds over dt is equal to 19. And it's going to equal to 19 what? Well, it's equal to 19 inches per minute. Alright, now let's take a look at our final example, which deals with rates of change using area. So a triangle has a base that is decreasing at a rate of 19 millimeters per minute, with the height being held constant. What is the rate of change of the area of the triangle if the height is 4 millimeters? Alright, so let's come on here, let's draw our triangle. So there is a triangle. And we're dealing with the area of the triangle, and we know that area is equal to 1/2 the base times the height. So that means in our triangle we need to label the base, which is going to be this guy, and then we need to find the height, which the height is going to be this guy. Alright, so we're told that the triangle has a base that is decreasing. So that means the base is going to be shrinking. And that means that if the base is shrinking, the area is also going to be shrinking inward. So this triangle is just going to get smaller and smaller and smaller. However, a key here is that the height is being held constant. So that means the height doesn't change. So when we take our variables and turn them into functions of time, the height is not going to change into a function because the height doesn't change. So let's go ahead and let's do that. So the area changes. So this is going to be area with respect to t equals 1/2 the base with respect to t times our h. And again, since our h is constant, it doesn't change, so therefore it is not affected by time. And then we want to find the rate of change of the area of the triangle if the height is 4. Alright, so now I'm just going to rewrite this equation here. So it's going to be a of t is equal to 1/2 h times b of t. And the reason I wrote it like this is because this 1/2 h is the coefficient of b of t. Now we're going to come in and we're going to take the derivative. So it's going to be d of a over d of t equals, and now when we take the derivative of a function as a coefficient, in the past we've said that we can just ignore the coefficient and rewrite it, because with the product rule, it would cancel out because it's going to be multiplied by 0. Then that's going to be times the derivative of b of t, which is db with respect to t over dt. So we have the change in area is equal to 1/2 times the height times the change in the base. Alright, so now let's just identify what these things are. So we have d of a over dt. And the question is asking what is the rate of change of the area. So we don't know what this value is. We know that h is equal to, the height is 4 millimeters, so that's 4. And then dr over dt, we know the triangle has a base that is decreasing at a rate of 19 millimeters, so this would be negative 19. And now we can just plug and chug. So dA over dt is going to equal 1/2 times 4 times negative 19. So dA over dt is going to be negative 38. And since this is an area, that means that our unit's going to be squared. So it's going to be millimeters squared per minute, or squared millimeters per minute. And that is our change in area. Our area is shrinking at a rate of 38 square millimeters per minute.